Okay, let's get started. Welcome back. Good morning, everyone. So last time we talked about power system operations, especially from ancillary service point of view. So the power system operator need to maintain the power system run all the time. So the power system security is important. The power system security means that when contingency happens, that need to be recovered immediately. And if it leaves out from a normal state, then it need to go back to the normal state again. So the balancing service means that the generation and the load must be equal all the time. Of course, we allow small deviation. So that is about 0.2 hertz in Korea. The 60 hertz is the nominal frequency, and 0.2 hertz deviation is okay. So to maintain to keep the system balanced all the time, we have different mechanisms. The first one was called regulation service, and the example was frequency regulation, FR. And another one is the load following service. That means the generator has a capability to follow the loads automatically. This kind of function is important, especially in microgrid. Microgrid is a small island, so the load fluctuates a lot actually. So the generator needs to change its output power to follow load. So this frequency regulation and load following service are used all the time. Okay, and FR, this is similar to fine tuning. If I use the terminology in AI, okay. But another types of service is contingency reserve, or simply this is called reserve. So this is from the operational point of view, these fine tuning types, the load following or frequency regulations are used all the time, but this reserve is actually reserve. The system operator has some reserved resource, and it needs not be used all the time, but this kind of reserve resource be ready for entering into the system when a contingency happens. Okay, so in that case we have a spinning reserve and non-spinning reserve. So the spinning reserve can be react immediately, like ESS is a pretty good spinning reserve type of resource. Actually, ESS is not called a spinning reserve. So spinning reserve, the example of spinning reserve is a flying wheel, for example. So when you Google flying wheel, you will find some image, and it has a cylinder, and in the cylinder you see a wheel, rotating wheel. Rotating means flying. So that's why the name of the spinning reserve is called flying wheel. So it has its kinetic energy all the time, and when it is connected to the grid, it immediately provide energy. So primary response, secondary response, and another types of reserve is non-spinning reserve. It takes more time to enter into the system. So use this kind of things when contingency happens. Primary response, secondary response from spinning reserve, and then non-spinning reserve. The gas turbine was turned on and it generates power. Okay, so so far we talked about balancing issue, and when we talked about this balancing issue, we assume that all the generators and loads and ties are connected to a single bus. That means we didn't consider power networks. We didn't consider the constraints. Okay, but next issue is about the network issue in contingency. So operators, transmission network and distribution network. So operator continuously performs contingency analysis, and what was credible contingency? Credible contingency means that when that contingency happens, still the system operator can keep the system operate in a normal way. So no credible contingency should destabilize the system. So that's why n-1 contingency analysis is important. Even if one element of the power system, like generator, transformer, or transmission line, has some outage, still the power system need to run. Okay, and so destabilizations, you can think this is kind of a disturbance. So thermal overload, transient instability, and voltage instability, these are the examples of destabilizers. And if a contingency could destabilize the system, the operator must take preventive actions. That's why, again, n-1 contingency analysis is important. And in Korean, that is called 상정사고. You may have heard this kind of terminology before. The terminology in Korean, in terms of power system, mostly came from Japanese. So actually understanding power system using English may be easier for some of you. Okay. 상정사고. What is 상정사고? What kind of 사고 is? what kind of? What is the English for this one? Yeah, contingency, outage, accident. Anyway, yeah, 상정. What is the meaning of 상정? The accident does not happen, but we assume that the kind of outage happens and see what happens. Okay, so that is the meaning of 상정사고. So when you look at this Korean, you don't know what it says, right? So English is better in that sense. Anyway, so yeah, so in n-1 contingency analysis perspective, preventive actions are important, and low-cost preventive actions are like this. Adjust taps of transformers. Transformers change the voltage from one side to the other side, and so what is it? OLTC. This is a type of transformer, on-load tap changer. So you know that transformer has a coil, not how can I say, one line, the other line, and we have a coil. Is it coil? No, this is ferro iron. Sorry. So, the inside of transformer we have some kind of iron, right? And the wires are surrounding this. Is it called coil or not? I don't know. Anyway, we have this kind of. This is iron, and we have this kind of wire, another kind of wire, and there is a ratio. How many times we have? Yeah, you know what I'm saying. So, but we have N2, N3, N4 depending on the point. So by changing the tap, we can change the ratio from N1 to N2 or N1 to N3 or N1 to N4, etc. That means we can change the voltage here, and that can happen on load. It is still connected in the network, and we can change the tap. So that kind of transformer is called on-line tap changer, OLTC transformer. And actually changing this tap is a mechanical action. So it has some constraints. We should not too much change this tap in a very short time. Okay. Anyway, yeah, winding, the number of winding. And adjust reference voltage of generators. 1.0 pu or 0.95 pu or 1.05 pu. Yeah, depending on the situation, and adjust the phase shifters. The phase shifters, from this name, you see that this phase shifter can change the phase, the angle between current and voltage. Okay, they are effective, low cost but limited, and high cost preventive actions. Actions are to restrict flows on some branches and requires limiting the output of some generating units and affects the ability of some producers to trade on the market. Because we limit the output of some generators, then that is about money. When the output power is limited by the operator, then the generator cannot get enough money by trading. So the example of thermal capacity and emergency thermal capacity and transient stability and voltage stability, these are the examples, but actually it's not quite clear what happens here. So let me skip this part and that part and this part again, but the voltage stability looks important. So actually so far we mainly focused on the balancing the system, the active power perspective. So this is active power, or this is about energy. We don't need it. So the frequency is associated with the balance of active power, the generation and total loads. Okay, right? But another part is the frequency is an important one, but another important one is voltage. Okay, and this voltage is related with reactive power. And so you will see voltage is controlled by injecting or observing reactive power. Injection of reactive power is by using capacitance. Okay, and observing of the reactive power can be done by a coil, or a generator can provide reactive power or observe reactive power. And that kind of things can happen by changing the phase between current and voltage. Okay, so you should recall yourself that this kind of diagram, this is a current and this is a voltage, and we have angle theta, and sometimes this angle is it depends on what is the reference, but we usually say, when this axis is current and this axis is voltage, and the difference between this voltage and current, that is denoted by theta. And sometimes we use the terminology lag, and sometimes we use the terminology lead. And inductance, L, coil, makes current lags the voltage. And the opposite case is the capacitance makes the okay, what I'm saying. Okay, so I think what I'm saying is this one. So this is a real power or active power, and this is a reactive power. Am I correct? Are you sure? Lag here or lag here? So when you are confused, the meaning of lagging and lead means that we have a resistance, we have a coil, and we have a capacitance, either serial or in parallel. Anyway, so C, R, L, C. Then we have a current, I. Okay. Then, using phasor notation, the impedance is R plus J omega L plus 1 over J omega C, right? So when the current is common, the current are common. The current is common for RLC because we have this serial connection here, okay? And the voltage here is Ri. The voltage here is J omega Li. The voltage here is I over J omega C. So when this current is common for all parts, the voltage applied for resistance, coil, and capacitance is same phase, 90 degree lead. Okay, sorry. The voltage has the difference between the difference of the voltage phase and current phase is 90 degree here, and then minus 90 degree here. Okay, and then why is it called lag and why is it called lead? It's because when you look at this, coil is it impedes current flows. Right? So when a voltage is applied here, this coil component impedes the current. So the phase of current is behind of the voltage. Do you see what I'm saying? So that's why this is called lag. The opposite of lag is lead. And the reason why this capacitance is called leading is because this capacitance has some energy already stored in this capacitance. So even if the voltage is applied here, it can immediately supply some current from the stored energy. Okay? So the phase of current can lead the voltage, intuitively speaking. So that's the meaning of lagging and leading. So in power system, I don't want to explain further, but by changing the active power, we can control the frequency. But by changing the reactive power, changing reactive power means that injection or absorption of the reactive power, and actually that is the meaning of that is changing this angle between current and voltage. Okay, so power factor 1, power factor 0. Power factor is cosine theta. Power factor. Actually, this kind of AC analysis is used in power system, but also in micro circuits. Am I correct? I think you already learned that in electromagnetism 1 or electromagnetism 2 or microelectronics 1, microelectronics 2, etc. Anyway, even in the small circuit, we have capacitance and this inductance component, right? So capacitance is important, inductance is important anyway. So yeah, injection or absorption of reactive power means to change this theta, the angle between current and voltage. When they are 90-degree difference, then zero active power can be delivered. Okay, and power factor is 0. So yeah, these are the examples, something like that. So in this case, we have a generator and loads, and no reactive supports at B. That means there is no reactive power injection or absorption can happen at this generator. So 198 megawatt can be transferred from A to B before voltage B drops below 0.95. However, the voltage collapses if a line is tripped. The meaning of line is tripped means that this line has outage, broken, is cut. Okay. And so the analysis omitted here. This is just the result. So when power transfer is larger than 166, and if a line is tripped, then the voltage here collapse. Voltage collapse means, we assume that the voltage should be 1.0 pu, but voltage collapse means that it quickly drops, so out of the normal range. So in that case, the maximum power transfer is thus 166 megawatt. But if this generator can provide 25 megawatt, so this is watt. Reactive power is and so active power or real power, active power, reactive power. Active power, reactive power, and what is it? What is the name of this? Active power, reactive power, and apparent power. And the unit of apparent power is what? VA. Yes, just VA. What? VAR? VA. So if the generator can support 25 megavar, then 190 megawatt can be transferred from A to B before the outage of a line causes a voltage collapse. So here you need to remember that something bad happens, outage happens on the line, voltage can collapse, but the generator, when the generator injects reactive power, it can mitigate voltage drops, voltage collapse. Okay. So voltage control and reactive support services. This is another kind of ancillary service. First type of ancillary service is about frequency, but the second type of ancillary service is about voltage and reactive support. So use reactive power resources to maximize active power that can be transferred through the transmission network. And some of these resources are under the control of the system operator, and the mechanism is mechanically switched capacitors and reactors, or static VA compensator, that is called SVC. So there is a hardware equipment that do that, static VA compensator, or somewhere you may see this kind of terminology before. StatCom. This is another hardware that can inject reactive power, and the purpose is to control the voltage, okay, and improve the power factor. Okay, so for example, if you are an owner of a factory, some manufacturing factory, and if the power factor of your factory is like 0.7, that means power factor is not quite good, then you can compensate that by installing this kind of equipment that provides reactive power, so that you can change the angle from here to there and improve the power factor. Okay, or transformer tap changers. But the best reactive power resources are the generators. So the synchronous generators, as you see, the turbine, the CC, C, C, G, T. This is what you saw in the 당인리 power plant. Combined cycle gas turbine. 복합 화력, you remember that, right? So this kind of, or steam turbine, this kind of synchronous generators can provide both active power and reactive power. It can change this angle theta. Okay? So depending on the situation, the generator sometimes can inject more reactive power if required. But that means increasing the reactive power means decreasing of the active power. So that's the loss of the revenue. Okay. And also the PV solar generation. We have a power electronics device. So the PV inverter changes from DC power to AC power, but while doing that, it also can adjust this theta. So solar panel, the inverter, also can provide reactive power and can control that. Okay, so obviously, if it wants to deliver the maximum amount of active power, this theta should be 0. But sometimes to change the voltage, it needs to support reactive power somehow. So it can change this theta angle. And if we assume an ideal thing such that the PV inverters can communicate with each other or can communicate to a centralized controller, then this controller can send some signal so that the PV inverter can change this theta. Then it can contribute to controlling the voltage in the distribution network. Okay, but that's the ideal case, and in reality, this PV inverter does not have communication equipment. Or, even if it does have that, there are numerous practical issues. Okay, but when you write a paper, we assume an ideal thing and devise a distributed control algorithm because we have a lot of distributed resources, PV inverter, ESS, blah, blah, blah. But in reality, when we try to implement this beautiful idea into the real system, actually in reality, sometimes they do not have communication function. reliability, their operational experiences. It's simple and usually ensures system security and quality of supply. But the disadvantage is that this is kind of mandate, and this is a rule, a restriction. That is not efficient typically. So from economist perspective, this is kind of wasting resources. So may provide more resources than needed and cause unnecessary investment. So kind of over provision. So that kind of resources are in waste. So not all generating units need to have control frequency, or not all generating units need to be equipped with a stabilizer. Okay? And also, this kind of compulsory provision discourages technological innovation. What is the original purpose of generator? Original purpose of generator is to provide active power, right? Yeah. But if we impose too much duty on provide reactive power, then the innovation of increasing the efficiency of providing active power is prohibited, for example. And generators have to provide costly services for free. This provide reactive power is a kind of costly service because it is at the sacrifice of reducing active power generation. But they should do that for free because this is mandate, right? Yeah. So think about this statement. Providing, so why? Why does providing reactive power increase losses and reduce active power generation capacity? I'm saying this is obvious, but why is that? Minjae, you understand the question? No, Kyungyong. What was the question? The question was, okay, you are a generator. I'm imposing a duty to provide some portion of reactive power, and that prohibits of producing active power. Why is that? Yeah, obvious, no. This magnitude is all the time, same all the time. So providing reactive power means that the cosine theta times this is reduced, right? So to provide the maximum active power, the power factor should be 1, right? Yeah, in this diagram, yeah, that is obvious, but intuitively, how can you say that? Think about it. Equity. How to deal with generators that cannot provide some services. For example, nuclear units cannot participate in frequency response, frequency regulation because nuclear power plant cannot adjust its output power. It is just constant generators at a cheapest price. Okay, so mandate all the same, all kinds of ancillary services to all generators is not efficient. So from economic efficiency perspective, this is not a good idea to force highly efficient units like a nuclear power plant to operate part loaded to provide frequency regulation service. And so it is more efficient to determine centrally how much reserve is needed and commit additional units to meet these reserve requirements. So not all the generators need to provide the same percent of reactive power. Okay? We should consider the characteristics of the generators, the types of generators. So compulsory provision is thus not applicable to all services. Yeah. So we need to think about market for ancillary services. And of course, we can have different markets for different services, and the long-term contract and spot market. And this long-term contracts is required for when the quantity needed does not change much, and so when it depends on equipment characteristics, that kind of ancillary service can be purchased in advance based on long-term contracts. The examples are black start capability, inter-trip schemes, as I told you, power system stabilizer, frequency regulation. But the opposite case is we need to buy this ancillary service from a spot market when needs change over the course of a day, and when price changes because of interactions with energy market. So buying the contingency reserve is a good example of obtaining ancillary service in a spot market. The required contingency reserve highly depends on the status of renewable generation, right? It depends on the weather conditions, so it changes over time. It changes every day, right? So we cannot have the kind of ancillary service in a long-term contract. It would be better to buy that in the spot market. We will see some example of that shortly. So system operator may reduce its risk by using a combination of spot market and long-term contracts, obviously. And the advantage of markets for ancillary services are it is more economically efficient than compulsory provision, and system operator buys only the amount of service needed, so no waste. Only participants that find it profitable provide services. So not all participants need to provide that kind of service. Only the participants who are willing to do that and who thinks he can make money or she can make money can participate in this ancillary service market. So it helps determine the true cost of services, and it opens up opportunities for innovative solutions. Good. But of course, we have some disadvantages of market for ancillary services. No, this will be more complex than energy market, and probably not applicable to all types of services, and potentially maybe there will be an abuse of market power, especially when there are only a few number of market participants. Okay, so example, reactive support in remote parts of the network. And in that case, market for reactive power would need to be carefully regulated. Okay, so let's think about then system balancing with renewables. Stochastic renewable require more reserve, as we discussed last time, and providing this contingency reserve from conventional generation may be technically difficult or impossible and expensive. So provide some reserve from demand side. This is called demand response. This is pretty effective. And let's look at this example. In this example, the installed wind capacity is 26 gigawatt, huge. And must run nuclear power capacity is 8.4 gigawatt. And CCGT, what was that? Combined cycle gas turbine, 당연히 발전소. So maximum 550, minimum 300. It has some minimum. Okay? And the demand is 25 gigawatt. Which country is it? Expected wind output, no, this is installed capacity, and this is the expected output, no, assuming some weather condition. And then in this case, the reserve requirement is computed by some formula to operate power system in a reliable way. Okay, this is the case. Then, yeah, this is expected output. The sum of this 18 gigawatt and 26 gigawatt. This is greater than that one, so it's okay. And also we have this CCGT. And then, okay, nuclear power plant has this capacity CCGT. One CCGT has a maximum and minimum. So when we have multiple CCGT, then how much is it? How many CCGT do we have now? Anyway, so the okay. The total demand is this one, 25 gigawatt, and sum of this, assuming wind power generation is 12 gigawatt, then this is constant. The output power of CCGT should be that, and the sum of this is 25 gigawatt. Okay. And by the way, what is it? Is it 9 point blah blah? Well, 8 point blah blah. Anyway, maybe we need to have 9 generators. And in reserve requirement is this much. So suppose that we provide this reserve requirement just using CCGT. And one CCGT can provide this minus that, 250 reserve. When we have one CCGT, it needs to generate this much minimum power, right? And this is the maximum power. So 250 is a reserve for one CCGT. You see what I'm saying? Okay, so 250, and the required one is 6. And what is it? 18? Use your calculator. Okay. So nuclear power plant, and then 18 times 300. Is that? No. What is it? 26. I'm sorry. Okay, good. Then 26 times 300 is this one. Okay. So the output power of CCGT is determined from satisfying the reserve requirement. You agree? So, and then the sum of this should be equal to 25 gigawatt. And actually, the wind power generation is random, and at the time, the wind power generation is more than that, so we need to curtail this amount. So the amount of wind power curtail is determined from the number of CCGT used to satisfy this reserve requirement. Yeah, 26. Yeah. And then, no, by the way, the CO2 emission rate and total CO2 emission is computed from running this gas turbine. That much. So the total power generation is that much. So we have a more carbon dioxide emission. But if we use demand response, and I forgot the number, so maybe check your textbook. So if some of this reserve can be provided from demand response, the reserve requirement from gas turbine is reduced, can be reduced. So that's this. Yeah. And finally, the wind power curtailment is also reduced, and the total amount of generation from gas turbine is reduced, so that further reduces the CO2 emissions. Okay. So demand side provision of ancillary service is a good way, and it creates a market for ancillary services. And actually, as you know, in Korea we have a demand response market already, and the total demand response capacity is actually, it increases, and check it on your own. I think it is like 7 gigawatt. I'm not sure. Yeah, it was 5 gigawatt before, but I think it increased further, so maybe 6, 7, or 8 gigawatt. So it opens up an opportunity for the demand side to provide ancillary services, and and advantage of demand side provision is that a large number of participants increase competition and lowers cost. So mostly large consumers, the factories, buildings, or the DR provider. Actually, the aggregator can aggregate that kind of DR resources and participate in the market. But ultimately, every household can also participate in this DR through an aggregator. So yeah, better utilization of resources. So providing reserve with interruptible loads rather than partly loaded thermal generating units, that would be better. Particularly important if proportion of generation from renewable sources increases. So yeah, demand side may be a more reliable provider, especially when large number of small demand side providers exist. And so there are two types of DR services. The first one is based on the DR capacity, and the second one is actual reduction of the demand when required. Okay, so as a DR provider, you can say, hey, I have this amount of capacity. Here the capacity means the capacity of reducing the consumption. I have this amount of capacity measured in megawatt. You can get money even if you do not actually reduce your load. But when a DR event happens, you must reduce that amount of load. You already have some contract. Then you have two types of revenue. First, from the capacity revenue. Second, for the energy revenue, for the amount of energy you reduced. Okay, so this capacity revenue is determined from your commitment, and this DR, you know what I'm saying. Okay. So yeah, let me stop here, and then